Today we also discuss one non-measurable set. Okay, obviously we talk about some definition of sum modulo 1 and translate modulo 1. Then we discuss one lemma. Okay, then we also going to be a non-measurable set. Okay, so first we write this one, that means sum modulo 1. Okay, here sum modulo 1 of two elements x and y. Okay, how we discuss this? So simply we define it, we denote it this one, and obviously here xy belongs to 0 1, 0 open 1. This one discussed by in this way: x plus y if x plus y less than equal to 1, and x plus y minus 1 if x plus y greater than equal to 1. They are less than 1. Okay, okay, then obviously we also denote this one sum modulo 1, and now we're going to discuss about translate modulo. Translate modulo 1 of some set E. Okay, E translate modulo y equal to those z. Okay, z equal to x sum modulo y, where xy belongs to what? E. Okay, xy belongs to E, or if x belongs to E, then this one is okay, and xy belongs to 0 1. Okay, here xy belongs to 0 1, here y belongs to 0 1, I think. Okay, then E, obviously what is E? E1 set. Okay, that means E obviously subset of 0 1. Okay, close 0 open 1. Then this one is happened. Now we're going to discuss about some lemma. Okay, related to this sum modulo 1 of x. We write this lemma now. Okay, we write this lemma here. Let E subset of 0 closed open 1 be a measurable set. Be a measurable set. Then for each y belongs to 0 1, then for each y belongs to 0 1, 0 closed open 1, the set E modulo y be measurable. Sum modulo y, that means this one is translate modulo y be measurable. Okay, be measurable, and obviously m of E translate modulo y equal to me. Okay, here we write this one E1 equal to E intersection 0 1 difference y, and e2 equal to e intersection 1 difference y1. Okay, e1 equal to this, e2 equal to this. Then e1 and e2 are disjoint measurable set. Are disjoint measurable set. Okay, whose union is E. Whose union is E. So ME equal to ME1 plus ME2. Okay. Then what happened? Now E1 plus some modulo, then translate modulo y equal to E1 plus y. Okay, and so E1 translate modulo y be measurable. Okay, and we have m of e1 translate modulo y equal to me1. Okay, and since m is translation invariant, since m is translation invariant, okay, then also here we write e2 y equal to e2 plus y difference 1. Okay, and so e2 translate modulo y is measurable. Okay, and m e2 translate invariant y equal to me2. Okay, then what happened? Then we write this one. Okay, as our portion. E translate modulo y equal to e1 translate modulo y union e2 translate modulo y. Okay, and the set are disjoint measurable set, and the sets e1 e2 are disjoint measurable set, are disjoint measurable set. Okay, hence what happened? Hence E translate modulo y be measurable. Okay, then what happened? Then M E translate modulo y equal to M e1 translate modulo y plus m e2 translate modulo y equal to m e1 plus m e2 equal to m e. Okay, now we are also going to this point where we prove this lemma. That means m translate modulo y be measurable and m translate modulo y equal to me. Okay, then we're going to discussion about a non-measurable set. Okay, also define further, and we're also going to discussion about a non-measurable set. Erase that portion. Okay, now we define in this way. We are now in position define a non-measurable set. Okay, how define a non-measurable set in this way? If x difference y be a rational number, okay, x difference y, okay, if be rational number, then x y are equivalent. Okay, b and be a rational number, be a rational number, then x and y are equivalent. Okay, that means this is an equivalent relation, and hence partition 0 1 where xy belongs to 0 1, and hence this is an equivalent relation. Okay, and partition 0 1 into equivalence classes, okay. Now classes such that any two elements of one class differ by a rational number. That is, any two elements of one class differ by a rational number. Okay, while any two elements of different class differ by a and while any two elements of different class is differ by an irrational number. Okay, by an irrational number. Okay, in this way we also define. Then what happened? By axiom of choice, there is a set P which contains exactly one element from each equivalent class. Okay, so by axiom of choice, okay, there is a set P which contains which contains exactly one element, from each equivalence class, each equivalence class. Okay, that means there is a set which contains exactly one element from each equivalence class. Then what happened? Then let Ri be, let Ri, where I equal to 1 to infinity, Ri be an enumeration of rational numbers, be an enumeration of rational numbers. Okay, in 0 1. Okay, with r0 equal to 0, and define pi equal to p translate modulo ri, then p0 equal to p, okay, p0 equal to what? P. And in this way we define this one, Ri be an enumeration of rational number, r0 equal to 0 and pi equal to p translate modulo ri, and p0 equal to 0. Okay, we define this one. Now we erase that portion and going to further discussion of that. Okay, now we're going to further discussion of that. Let x belongs to pi intersection pj. Okay, then x equal to pi, this translate modulo ri, equal to again pj translate modulo rj. Okay, with pi and pj belonging to p and pj belonging to p. Okay, and but pi difference pj equal to ri difference rj. Okay, is a rational number, okay, hence what happened? Hence pi equivalent to pj. Okay, rational number. Since p has only one element from each equivalence class, since p has only one element from each equivalence class, then what happened? Then we must have I equal to j. Okay, this implies that if I not equal to j, pi intersection pj equal to 5. Okay, that is pi is each pairwise disjoint sequence of set, each pairwise disjoint sequence of sets. Okay, so what happened? So we also see that pairwise disjoint sequence of set. Okay, now on other hand, each real number x each real number x in closed 0 open 1 each in some equivalence class some equivalence class. Okay, and so is equivalent to an element in P, and so is equivalent to an element okay, in P. But if x differs from an element, if x differs from an element in P, by a rational number Ri, then x belongs to Pi. And thus union of Pi equal to closed 0 open 1. Okay, now we erase these portions also. That means each real number x in 0 1 closed 0 open 1 is in some equivalence class, so is equivalent to an element in P. But if x differs from an element in P by a rational number Ri, then x belongs to Pi, and union of Pi equal to closed 0 open 1. Okay, now we erase that portion and going to further discussion of that. Since each Pi is a translation modulo 1 of P, is a translation modulo 1 of P, Okay, each Pi will be measurable if P each Pi be measurable if Pi be measurable each Pi be measurable if P is okay, and we'll have some measure we'll have same measure and we'll have same measure okay. But if these were the case, but if this is the case, then m of closed 0 open 1 equal to summation I equal to 1 to infinity m of pi equal to I equal to 1 to infinity m of p. The right side is either 0 or infinity depending on whether mp is 0 or positive, and the right side is either 0 or infinity, is either 0 or infinity depending on is either 0 or infinity is depending on whether mp is 0 or positive. Okay, but this is impossible. Okay, this is the case if m is this one equal to, but the right side is either 0 or infinity depending on whether mp is 0 or positive. Okay, so what happened? So this is impossible, this is impossible. Okay, hence what happened, this is impossible since so easily m of 0 1 equal to 1, then p cannot be measurable, then p cannot be measurable. Okay, so we get a set p which cannot be measurable. This set is how this set is defined. So simply we first defined some equivalence relation, xy difference a rational number, then we defined some, that means same in belongs to same class, difference of two elements, difference a rational number and different class, then an irrational number, then a set which contains exactly one element from each equivalence classes. Okay, this equivalence class, then this set p is defined in this way, one element from each equivalence class, then this set p form. Okay, and we also handle this one, and we also going to see that a non-measurable set, p be a non-measurable set. So today we stop here.